So far we've looked at finding unknown standard deviations and unknown means, and now we combine the two. Well, we don't know the mean and we don't know the standard deviation. Let's have a look. Okay, so here's the sort of question where we don't know either. The heaviest 10% of pairs weigh more than 170 grams, while the heaviest 20% of pairs weigh more than 155 grams. Find the mean and standard deviation. So, okay, a sketch. Before we do anything else, a sketch. So here's the distribution. And what we're told then is this. We're told that the heaviest 10%, okay, we'll just put in the mean, but we don't know what it is. The heaviest 10% weigh more than 170 grams. So I'm just going to deal with this one first. So just like in the previous cases, my question is, how many standard deviations above the mean do you need to go to get to the top 10%? So it's the standardized normal distribution again, which helps us out. So that's our Z distribution, Z with a mean of 0 and standard deviation of 1. And the question is, how far up do you need to go to get to the top 10%? So we can get that from the calculator really easily. Here's how. So you see me do this a bunch of times now. The top 10% has an area to the left of 0.9, and we can see it's 1.28155. So that is 1.28155. So you need to go 1.28155 standard deviations above the mean to get to the top 10%. So that means that 170 is the mean plus 1.28155 standard deviations. Well, there's an equation with two unknowns. We can't solve that, but we've only used half the information. We've not used the fact that the heaviest 20% of the pairs weigh more than 155 grams. So I can just do exactly the same trick again, but with 155. That should capture the top 20%. So using my standardized normal, I'm just going to search up and say, how many standard deviations do you need to go above the mean to get the top 20%? 20%. So it's obviously going to be not as far above the mean because it's not going as far out on a limb as the other one. So what is it? Let's have a look. So the top 20% is going to be an area to the left of 0.8. And that is 0.84162. 0.84162. So that means that that 155 was the mean plus 0.84162 standard deviations. Well, look, two equations, two unknowns, is simultaneous equations. And in fact, it's a pretty easy one because you've got mu sitting there in both. So if we just subtract these, the mu's will cancel. 170 minus 155 is 15. And now we've got 1.28155 standard deviations minus 0.84162 standard deviations is 0.43993 standard deviations. Divide both sides by that number, 15 divided by that, and you get a standard deviation of 34.1. And what does that mean for the mean? Well, we can just sub it into either of these. So I'll sub it into this one at the top. So I've got that 170 is the mean, which I don't know, plus 1.28155 lots of this thing that I've just worked out. So 170 is the mean plus that number times 1.28155, which is 43.696, and that means that mu is 170 minus that number, which is 126.3. So once again, you want to just check it makes sense. Were we expecting a mean to be around that? Well, sure, because look, we've got the top 10% are bigger than 170 and the top 20% are bigger than 155. So we would expect the average to be below that. So if you don't know either, you form two equations, then it's simultaneous equations. Let's have a look at another example. So unknown mu, unknown sigma. Given that probability that y is less than 5 is 8% and probability it's greater than 8 is 32%, calculate the value of mu and sigma. And I really do encourage you to pause the video and try this one yourself first, because you've seen plenty of examples now. All right, so we don't know the mean. Now, probability being less than 5 is 8%, so 5 is quite far down here, and that there is 8%. Probability being greater than 8 is 32%, so that's going to be something like this, where that is 32%, and this point here is 8. So, how far below the mean do you need to go to get the bottom 8%? Just use the standardized normal. So the standardized normal is where z is normally distributed with mean 0 and sigma 1. It counts the standard deviation. So where's the bottom 8%? Calculator's out, and it's an area of 0.08. So that's minus 1.4051. Minus 1.4051. And what about the top 32%? Here, let's just do it on the same diagram. Well, back to the calculator. Well, the top 32% has an area to the left of 0.68. So that is 0.4677. 0.4677. So what does that tell me? It tells me that 5 was reached by doing the mean minus 1.4051 standard deviations, and the 8 was reached by doing the mean plus 0.4677 standard deviations. There's our simultaneous equation, and we solve it however we like. I'm actually going to do the bottom equation minus the top one to keep things positive. 8 minus 5 is 3. Mu minus mu is 0, that's the whole point, and 0.4677 minus minus, so plus 1.4051, is 1.8728 standard deviations. And now we find the standard deviation by doing 3 divided by that number. And that's 1.602. How do we find the mean? Just sub this back in. So I'll sub it back into the first one. 5 was the mean minus 1.041 minus 1.4051 times my newly found sigma. So 5 was mu minus 2.251. By the way, I'm keeping sort of fully accurate answer on my calculator and just using the answer button. It's a good strategy to not lose accuracy marks. Add that to both sides, and we get mu of 7.25. Were we expecting something like that? Sure we were, because we knew from our reasonably good drawing that mu was somewhere between 5 and 8. Okay, one last example, and please do pause the video and try this one yourself. From experience, a high jumper knows that he can clear a height of at least 1.78 meters once in 5 attempts, 20% of the time that is. He also knows that he can clear a height of at least 1.65 meters on 7 out of 10 jumps, so 70% of the time. Assuming the heights of high jumper can reach follow normal distribution, draw a sketch to illustrate the above information. Okay, so the above information is this. So here's the normal distribution, and we do not know the mean or the standard deviation, but we do know that he clears 1.78 meters 20% of the time. So here's 1.78, and that there is 20%. We also know that he clears 1.65 meters 70% of the time, which means we've got 30% over on this side. Can we find mean and standard deviation? That's part B. So this was part A. Part B we're going to need more room for. So here's the information that was given. I've just summarised it. He clears 1.78 metres 20% of the time, and he clears 1.65 70% of the time. So our usual stuff, here's just the sketch again. So it is, 1.78 was here, and that was the top 20%. And 1.65 was here, and that was the top 70%, but the bottom 30%. Okay, now we're going to use our standardized model as usual. So a little sketch of that. And we want to find where's the top 20% and where's the bottom 30%. So calculators for that. So normal inverse, let's do the left-hand side one first. So the left-hand area is 0.3. So that's minus 0.5244. Minus 0.5244. And for the top 20%, well, top 20% is an area to the left of 0.8, and that gives us 0.8416. 0.8416. So what does that mean? It means that 1.78 metres was found by taking the mean, which was here, and going up by 0.8416 standard deviations. And it means that 1.65 was found by starting at the mean and going backwards, so the mean minus 0.5244 standard deviations. Solve this as we did the others by subtraction, so that minus that is 0.13, 13 centimetres. The mu's cancel, and we've got 0.8416 minus minus, so plus 0.5244 standard deviations. Gives me 1.366 standard deviations. Okay, so I get a standard deviation of 0.13 divided by 1.366. So my standard deviation, they asked it to 3 decimal places, is 0.095. I'll keep the kind of more accurate answer on my calculator. Now for the mean, I can say that 1.65 was the mean minus 0.5244 times by this standard deviation I just got. So that's 1.65 is the mean minus my standard deviation times 0.5244, which is 0.0499. So that means that my mean is 1.65 plus this answer I just got. So I get a mean of, well, my calculator is saying 1.6999, so to 3 decimal places, that is 1.7. All right, does it make, I guess 0, 0 to make it properly decimal places? Does it make sense? Sure, because look, I was expecting an answer somewhere between 1.65 and 1.78. Okay, quite an advanced method there. Hope you enjoyed looking at it. I'm going to see you for more normal distribution stuff in the next video.